Okay, so Lourdes has created the following challenge for you. She has given you 3 of the 4 points necessary to determine a rectangle on graph. She wants you to find the points that complete each of the rectangles below, then calculate the area of the rectangles from parts A, B, and D. So for A, B, and D, we're going to find the area, but she doesn't expect us to find the area for C, at least not yet. For A, I've got these points, and I've already pre-plotted them, right? I've got one at -1, 3. I've got one at -1, 2. I also have a point at 9, 2. And I believe that our final point would have to be right here, and that is the point 9, 3. So I think for A, we would say our extra point would occur at 9, 3. And then we're also supposed to find the area. Well, if I'm looking at the area for this one, it's a rectangle. One of the dimensions is 1. The other one is 9 plus 1. I believe this is just 10, right? This is 10 long. So if I go from 1 minus, or rather 9 minus 1, which would be a positive 10. So this has an area of 10 square units. So the area for A is 10. It doesn't say what these units are, so I'll just say units squared. Okay, so for B, let's look at it now. For B, these are pre-plotted points right here. You can see I've got one at 3, 7. I have a point that's located at 5, 7, and I have one point located at 5, -3. The fourth point would have to live right here, and that is the point 3, -3. I'm kind of starting to see a pattern here on how I can figure these out without necessarily plotting them. So it appears that this would be my rectangle, and the dimensions of this is 2, and I'm going from 7 to -3, which is a length of 10. So this is 2 times 10, which would be an area of 20. So for this problem, for part B, we have that it is, this point, if the third point was located at, -3, 3, -3, so over 3 and then down 3, and the area would be 20 units squared. All right, now let's do C. C, they're not asking us to find the area. Here's the points pre-plotted, and you can see they're all listed in blue. Now this next point is it's somewhere in this region down here. Where exactly? Well, if I just follow this slope pattern, look at this. I go down 2 over 1. So right here I can go down 2 over 3. 1, 2, 3. This is the point right there. Down 2 over 3. So I'm looking at -2, -7 for C. -2, -7 would be where C is. This is my rectangle then, right? This rectangle is on a diagonal, and I suspect the reason why they've asked us not to find the area is I think they're afraid that we couldn't find the area for the length of these. But I think it's just an application of the Pythagorean theorem. I think we could do that, but they didn't ask us to find its area. Okay, so the final question then, D. There is no way we're going to plot this. In fact, let me clear the screen here. On D, we're not going to plot it. It's too large, but I want to kind of sketch where the things are at. And if I have a sketch, I think I could figure out the rest of it. So one of the points is at -52, +73. I'm just going to put some point up here, -52, +73. Maybe I'll write the coordinates. Then the next point I have is at +97 and then 73. So right here, +97, 97, and then up 73. Okay, so I think I see one of the sides of my rectangle, perhaps. The next one I've got is at 96 and then 1,483. Okay, so I'm not going to go all the way up here, but it is 96. This was supposed to be a 96, not 97. 96 +73, because now I'm at 96, and then I'm at this large number, 96 +1,483. This looks just terrible. Let me clear that and sketch it one more time. I'm going to try it one more time. now that I see relatively where things are at. So I've got this point at negative 52, 73, and then I've got a point at right about here. I'm going to call this one 96, 73. And then the next one is 96 and a huge number. It's 96, 1483. And then this last point right here, I pretty much got, I have what it is, right? Its x value is going to be this x value, so it's going to be negative 52. And its y value is going to be 1483. So this is at negative 52, 1483. So there we go. So that's my rectangle. The question is, well, what the heck are the dimensions of this rectangle? Well, let's see here. The dimensions of this rectangle, if I look at it, I'm going from negative 52 all the way to positive 96. So if I was to do, for example, 96 and then subtract from that a negative 52, that's 96 plus 52, and for convenience I'm going to write it there. Let's see, 6 and 2 is 8, and this is 148 units long. So one of my dimensions is 148 units long. And then if I want to find the other one, you can see I'm starting at 73 and I'm going up to 1,483. So this distance right here is just the difference in those numbers. So I'll take 1,483 and I'll subtract the 73. 3 minus 3 is 0, that's a 1, a 4, and a 1. So this has dimension 1,410. Now the area of that rectangle then would just be the product of those two numbers. In other words, 148 times 1,410, which I believe is 208,680. So this is the area. Definitely would not want to try and find either the points or the area by plotting them, but this was the point that was missing, 52 and 1483, and the area of this beautiful rectangle that's quite large is 208,680. Okay, super fast, super fun, super easy. On graph paper, graph each of the lines below on the same set of axes, and then it's going to ask me some questions about the relationship between lines. So let's start with A. A has a y-intercept, I'll do this one in red, a y-intercept at positive 4, and a slope pattern of up 1 and then over 1, 2, and 3 units. So up 1 over 1, 2, 3, up 1 over 3, etc., up 1 and over 3. I can also go down 1 and back 3, 1, 2, 3, to kind of get a, if I want to extend the pattern that way. So if I'm taking a look at it, I think this is pretty accurate. I'm trying to draw a line that goes through there. I might try and extend it a little further this way, but that's a pretty good representation of that particular line. Let's do B. We'll do it in a beautiful green. So in B, our y-intercept is 4 again. They're both crossing at 4. This one has a slope pattern of down 3 over 1. So I'm going to go down 1, 2, 3, then over 1, down 1, 2, 3, over 1. And I see immediately what's going on here, right? These slopes are opposite in sign. One's positive, one's negative, and they're also reciprocals. So we could say quite comfortably that these lines are perpendicular to each other. They're meeting up at each other at a right angle, 90-degree angle right there. That's probably one of the questions. Let's do C, and for C I will use blue, and C has a y-intercept down at -2, and we're following the same pattern, slope pattern as B, so I'm going down 3, 1, 2, 3 units over 1, down 1, 2, 3 units over 1, down 1, 2, 3 units over 1, and I could also go, up 3 and back 1. So this is the, I hope this is it. Does this look like the line? Something like that. There and there. Okay, so now let's answer the rest of these questions. It says, what is the relationship between lines A in red and B in green. Oh, that's easy. These lines are perpendicular. That's the symbol for it, right? This upside down T. So A and B are perpendicular. Probably should have wrote that A and B. These lines are perpendicular. Let's see, the other question they said is, what about between B and C? Oh, let's see, B and C. Oh, the lines B and C are parallel. This is symbol for parallel, like that. Parallel. Parallel. Okay. Let's see, while solving x over 6 equals 5 halves for x, Nathan noticed that x is divided by 6. What can he do to both sides of the equation to get x alone? Well, I would say, hey, if x is being divided by 6, I would suggest that he multiply both sides by 6. That'd be fun, multiply both sides by 6. It says solve for x. Okay, let's do that. So for b, I've got x over 6 equals 5 over 2. And I'm going to multiply both sides of this, both the left and the right side, by the number 6. So I'll just put a, do it like this, 6 over 1 here and 6 over 1 there. So both sides are picking up a factor of 6. And you know what, I'm going to show this like that. There we go. So on the left-hand side, when 6 times x divided by 6 is just simply the number x. And over on the right-hand side, that equals 5 times 6, which is 30 over 2, which is 15. So x is the number 15. That's great, right? Now see, C says use the same process to solve this equation. Okay, so let's make a little room for question C. I'll put it right here. The equation for C is x over 10 equals 2/5. You know what? I'm going to choose to multiply both sides by 10. I like it. So times 10 over 1 times 10 over 1. And over here, let's see, 10 times x is 10x divided by 10 is just plain old x. Now that I've got x there, let's see, 2 times 10 is 20, 20 divided by 5, 20 divided by 5 leaves me that x has to be the number 4. So x is 4, and sure enough, 4/10 is the same thing as 2/5, so not bad. Write the following numbers in scientific notation. Remember, scientific notation is going to have a single leading digit, so I've got 3.7, right? So that's the correct form. Now, in order to get this number to equal the same thing as A, I need to multiply by many factors of 10, right? It has to be 3.7, but it's large. So there's many 10s that I multiply by, and I can just count, you know, if I multiplied by a single 10, it would give me a 37, and then it would give me this here, and then, so I need to multiply, let's see here. This would be 1 10, 2, 3, 4, 5, 6, 7, 8, I believe. 3 times 10 to the 8th power. And you know, it's a little tricky to see that. Probably it might be nice if I wrote this larger. 3, 7, 0, and then I've got 1, 2, 3 zeros, and 1, 2, 3 zeros. So I've placed the digit right here, right? And I need it to be way over here. This is where it needs to be. And every single time I multiply by 10, it just jumps 1 to the right. So that's 1 of the 10s, 2, 3, 4, 5, 6, 7, and 8. So it is 3.7 times 10 to the 8th power. Luckily, B looks a lot smaller to deal with. So the correct location would be 7.6, but again, I need to multiply by some powers of 10 to put it back in the right spot. This number is 7,600. I've placed the decimal right here, but I need it to be here. In order to get it over there, I'm going to just go by 1 10, 2 10s, by 3 factors of 10. So this would be 7.6 times 10 to the 3rd power. So there are my two answers here and here, both in scientific notation and both numerically identical to A and B. Chi loves to read. He can speed read rather 40 pages in 3 minutes. How long should it take him to read The Scarlet Letter, which is a 625-page novel? So we're going to solve this with a proportion. Our answer will probably be expressed in minutes, and if I want, we might consider converting those minutes then into like hours. So let's set up our proportion. So we can read 40 pages per 3 minutes. So every single time, 40 pages in 3 minutes. We're reading this novel that is 265 pages, and the question is how many X minutes will it take? Well, I'm just going to say right now, if you look at it, X, the unit for X will be minutes when we solve it. So I don't need to float these units around right now. I'm just going to write 40 over 3 equals 265 over X. The first thing I'm going to do to both sides is I'm going to multiply both sides by the number X to get it out of my denominator. I don't like working with the denominator, my variable in my denominator. So when I do that, this equation becomes 40 times X over 3 equals 265. You can see X over X is a giant 1 on the right-hand side, so I'm left with just 265. I'm going to multiply both sides by 3 now. When I multiply the left-hand side by 3, I'm left with just 40x because I've got, again, a giant 1 of 3 over 3. And over the other side, when I multiply 265 times 3, I get the number 795. And yes, I use my calculator, and I'm not ashamed to admit it. Let's see. Now what I'm going to do is go ahead and take and divide both sides of that by 40. So let me rewrite it. 40x equals 795, and divide each side of this by the number 40. On the left-hand side, I have just x, and on the right-hand side, I have 795 over 40, which is, it's not an hour at all, right? It's only 19.875 minutes. M-I-N-U, just minutes, right? So that's pretty darn fast. Now, if I want to verify that, if I multiply 18.875 times 40, if I multiply this just by 40, you should get the right, yeah, I do. I get, I'm suspicious of this answer. I'm trying to think here. 40 divided by 3 should be the same thing as 265 divided by 19.875. And indeed they are. They're both exactly 13.33333. So that's my unit rate, by the way. It's 13 1/3 pages per every minute, and it's going to take me, less than 20 minutes. This person, I can't read this fast, but less than 20 minutes to read this book. But the question is, do you understand what you've read? I don't know. So I've got this hexagon totally set up, and it's gone through a rotation of 0 degrees. And you can see as I start rotating it around, right? So there's 23 degrees, 34, 43, and right here around 60 degrees, you can see it's locked back into itself, right? And in fact, if I go another 60 degrees, that would land us around 60, and 60 is 120. Right around 120, it's back to the same thing. And then if I go through, as this question asks, through 180 degrees, it's right there at 180. It's locked in again. So basically, whenever we observe this happening, this object has what we call rotational symmetry. And as I rotate about this origin, or the center of this object, every 60 degrees, it's going to be back where it started again. So in fact, you could say, hey, if x is some number, or if n is some number, 60 times n would be a value where I could rotate it and stop, and it would lock in and be symmetrical again, or it would line up with itself again. Anyways, rotational symmetry. So if you haven't done it, you should definitely pause the video, jump back, and read the math notes about polygons in lesson 3.1.2. Go back and read it. At right is a diagram of a regular hexagon with center at C. We copied this onto your paper and then complete the problems below. It says draw the result of rotating the hexagon about its center 180 degrees. On the previous slide we just explained what happens, right? Anytime we have a multiple of 60 degrees, this thing lines up with itself again. So at 60, 120, etc. And whenever this happens, this is what we call rotational symmetry. The next one says, what is the result when the original hexagon is reflected across the line N shown at right? Well, you can look at it. When I reflect that down across it, you can see it's going to match itself exactly, right? And when this happens, line N is called a line of symmetry, and we have what's called reflectional symmetry. And then part C says, does a regular hexagon have any other lines of symmetry? That is, are there any other lines that you could fold across so that both halves of the hexagon would match exactly the same? So we already looked at this one. This is the one that they had. Excuse me, it's not a perfect line. But you know what? Actually, any of these diagonals would do that. So I could fold it across this line, and it would work. I could fold it across this line, and it would be the same. And actually, I could fold it just right down the middle like this, right? If I fold one half onto it, that would line up perfectly. And while I'm doing that, I could also fold across this one, and I could also fold across this. So each time I did one of those folds, right, those would be an additional line of symmetry. And it says how many, find as many as you can. Well, if I'm starting here, right, I found 1, 2, 3, 4, 5, 6. Now, I will not count this one again because I already counted it over here. So it's just those 6. So I believe I have 6 lines of symmetry for a regular hexagon.